All right, so we're looking at 11.4, three-dimensional figures. We've got 5 shapes there. They're called polyhedra or polyhedron. I've got examples of them. Here is an example. I know it's small, but it's an example of a tetrahedron. It has 4 triangular sides. 4 triangular sides. Now, if I was to roll this dice, the answer would be whichever one it lands on, because otherwise the other one's just a point. So that would be that's called a tetrahedron, 4 triangular sides, like a pyramid. We would call that a triangular pyramid as well. The second one is a cube, but you've seen cubes before. I do have an octahedron. Octahedron has 8 sides. So you see 4 triangles around the top, and then you got 4 triangles around the bottom. And that's got 8 faces, 8 sides. Octahedron, 8-sided figure. That's that one. We also have a dodecahedron that has 12 sides. Each side on this one is a pentagon. So to get those to fit together perfectly, to have 12 of them, they had to have pentagons as the sides. And there are 12 sides, so it's called dodecahedron. Now the hedron means it's a solid and there's no curves in it. They're all straight sides. The last one, icosahedron, has got 20 sides. No, icosahedron has 20 sides. And I have one of those too. Each side is a small little triangle. And it does work. The dice would work. You could roll the dice, and whatever side is up on the top, it'd be the side that you want. That would be an 11 if I rolled. So that would be called icosahedron. Now, all of these shapes have 3 things in them. They all have vertices, they all have edges, and they all have faces. I'll go back to this blue one, the octahedron again. Okay, and the blue one is in the middle of the chart right here. It has 4 faces around the top, and it has 4 faces around the bottom. So the faces here, the very last column in octahedron there is 8. It's got 8 faces. Now a vertice is a point. So can you see that if you were to touch this dice, there's a few places where if you push on it, that's a point. That could hurt when you push on it because it's pointing right into you. Those are vertices. That's where 2 or 3 or more faces come together and they make a dot, they make a point. Okay, in this one, there are 6 of them. There's a point on the top, there's a point on the bottom, and then there's 4 points around it. So there's six vertices. So you can see there's the 6 vertices. The last thing they have are called edges. And edges are where 2 faces come together. It's like your desk, where 2 sides come together, you have an edge. That's called a line segment. It's a line segment because two sides come together, make an edge. This one has 4 edges on the top, it's got 4 edges around the middle, and it's got 4 edges on the bottom. So it has a total of 12 edges. There is a relationship between these. The relationship between the faces and the vertices and the edges is that if you add 2 to your edges, so I had 12 edges, if I add 2 to it, I would get 14. Okay, now that's going to be the same value as your faces and your vertices together, and if you added 6 to 8, you would get 14. So that is a theorem that actually works. Faces and vertices together is the same thing as your edges plus 2. That was discovered by a Swiss mathematician called Leonhard Euler, born in the 1700s, and he found out that if you take your faces and your vertices together, it's going to equal your edges plus 2 every time. Any polyhedron shape, that will happen. The reason that comes in handy is if you're trying to figure out how many faces something has and you know the vertices and edges, you can solve it. Or if you want to solve for edges, or if you want to solve for vertices, you have those in there to solve. All right, let's get to your vocab. I know there's a few of them. They're short. I just made them as short as I could for you. Polyhedron, 3-dimensional with all faces as polygons. Poly is many. I put in there no curves. You cannot have curves in a polyhedron. I told you what a face, edge, and vertex are, so you can get those. Your face is one side. Your face is going to be a polygon. It's going to be a side that has no curves in it. So faces are going to be polygons. An edge is a line segment. It has to stop where the two sides come together. It's a line segment. And the vertex is the point where three or more faces come together. I should change that to 3 or more, because you might have some where there's more than 3 faces. Now you have a few questions in today's extra practice about cross sections. You're going to see what that is in a second, but let me give you a little illustration. So you've got this cup. Okay, now if you were just looking at it straight head on, you would see a circle, correct? If I was to slice it vertically and take that part off, you would still see a circle. The cross section would be the same. It would be the exact same shape. Now, if you were to slice it diagonally, now you might see a rectangle or something different. Okay, so a cross section is basically the shape that you see when you cut a plane through a polyhedron. What shape is formed when you slice it through? There's a couple of them that you'll see on the extra practice that are pretty easy, I think. Solid of revolution, I kind of try to show you here. Do you see this picture of a right triangle? Yeah, you got a right triangle right here. Oops, that was not smart. So you got this right triangle right here, okay? If you take that right triangle and you put it on like a pencil, you cut it out, you put it on a pencil, and you spin the pencil really fast. Spin it so fast it'll look like a cone, because it's going, the bottom will be going around a circle, and so that'll make a bottom circle. The top is touching the axis, so it won't move anywhere. It'll just be the point. Okay, so that could be a cone. They have some other names here. The rectangle, though, is the one I wanted to show you. If you spin a rectangle around really fast, the top will be a circle, the bottom will be a circle. They'll be the same circle. So it has to be a cylinder. It has to have 2 circles on it, so that would be a cylinder. You got a couple others you can see. If you had like an oval, you'd make an oval shape there, egg shape there if you had a half circle or half part of a half circle. So just things that would make solids. When you spin it around, it would make a solid. What solid would it make? And the axis of revolution would be that line or that pencil that you were spinning. Whatever is symmetrical, whatever would be the same on both sides, would be your axis of revolution. All right, that takes us to the pictures of the 5 shapes that we are going to be focused on the most over the next couple of days. Those 5 shapes, 2 are polyhedra. You can see the 2 polyhedra right there. And 3 of them are not polyhedra because you can see the curves in them. We are going to find volume and surface area of those shapes starting Monday. They're just formulas. All you got to do is plug it in. So you got to find the measurements and plug it in. So we're going to be just looking at the formulas for those 5 shapes. Okay, those go pretty quick. Volume of them, how much would it be to fill them up? And the surface area would be how much to cover them. You're wrapping a present and it was a prism, how much paper would you need to wrap? That's called surface area. All right, in this extra practice, they want you to tell which one is a polyhedra. And if it is, what is it? This first one was yes, that's an octagon, or octahedron, I mean. That was the blue one that I showed you. And the second one was definitely no, it was a donut, so that's definitely not a polyhedra. Definitely not. If you go to the cross sections, You see the cross sections here? If you were to take that pyramid, okay, that's the black little dice that I showed you earlier. If you take that pyramid and you sliced off the top horizontally, if you cut it off horizontally, you would see then a square. The tip would be gone and you would see a square because the bottom base is a square. If I did that to this pyramid, if I sliced it off here, since the base is a triangle, I would see a triangle. I wouldn't see a square. And this one I would see a triangle because the bottom would be a triangle. If you slice the same pyramid vertically, you would end up seeing the triangle. You would see the triangle part from the back side of it. If you slice the same pyramid diagonally, cutting it inwards, you would see that these two are going to be going outward, and then you'd have your two parallel bases. So you'd have a trapezoid. And then 6, you would see the same thing on 6. Because you'd be slicing that vertically through it, you would see the same thing in front like the cup. You saw the circle, and then you saw the circle again. This one, you would see the heptagon in the front, and then you'd see the heptagon again if you sliced it. The last two are just describing what shape you would see if you spun that around really fast. If you spun this one around really fast, this would be a cone if it was a triangle. If this whole thing was a triangle, then it would be a cone. But the triangle is not complete. You have this piece here that would be like cutting off the tip of the cone. So it would be like a cone with the top cut off. Okay, so that was 7. And number 8 was, if you drew a line right in there, I think you would be able to see better what this is. This is a cone on top. So this would be a rectangle. So the triangle's on top, and if you spun a triangle, you'd get a cone. On the bottom, you have a cylinder because the bottom's a rectangle. So it's a cone on a cylinder. It'd be like two shapes together if you spun that. It would be a cone on top of a cylinder. All right, you will need these formulas today for your area quiz. So I rewrote them in case you forgot them. Because I know you've seen these before, probably back in 5th, 6th grade. They showed you area formulas. Area of a trapezoid. I know for a fact there's a trapezoid in today's section. So you want to make sure you get the area of a trapezoid. Add the two bases together, and those are the two parallel sides. And then times it by the height, and then divide by 2. That's a trapezoid. Area of a circle we did already, pi r squared. Rectangle is easy, base times height. Make sure you have a right angle for your rectangle or your parallelogram. You got to have a right angle. Kite we did yesterday. Kite and rhombus. Diagonal times diagonal divided by 2. We did a kite yesterday on your Mentimeter where you had to add the two diagonal, find the two diagonals, multiply them, divide by 2. We also did the regular polygons yesterday. 1/2 times little a times big P, and we did that today too on those ones we went over. So 1/2 times little a times big P, perimeter. Big P is perimeter. Square, you could also use rectangle, base times height, or you could just do side squared if it's a square. Now there are 2 areas of triangle formulas. I don't know if you remember the second one. I'm pretty sure you remember the first one, base times height over 2. But we learned one with trig. We said that if you have SAS, if you got a side, an angle, and a side, you could do the 1/2 times A times B times sine of C formula. But you have to have SAS there. You have to have the sides and the angle in between them. The C has to be in between the A and the B for you to get that formula. Otherwise, just do base times height over 2. You'll have your area of a triangle. The last thing you're going to need that deals with area is what we call geometric probability. Geometric probability is like throwing a dart at a dartboard. What % chance does that dart have of hitting certain sections, certain parts of that circle or parts of whatever the dartboard shape is? So if this was not my dartboard right here and I had a white dartboard with red circle and green circle, what's the probability of each color? What percent chance do I have of getting in the dart if it hits the board? It would be in each color. To do that, you need to find the area of the color you want and divide that by the total area. That's just easy. Get the area you're looking for, divide it by the whole thing. In this shape, the whole thing is going to be a 7 times a 9. That's going to be the total area on the bottom of all three fractions, because that's our whole dartboard, 7 times 9. Okay, so the area of the red one, if I'm looking for the red probability, area of the red is just pi times 2 squared. My radius is 2. Pi times 2 squared would be 12.57. My whole area, the whole thing, would be 7 times 9. That's 63. If I take my area that I want and I divide it by 63, the total area, I get 0.1995 as a decimal. If you want your probability as a decimal, you'd be done. If you want your probability as a percent, you got to multiply it by 100. Multiply it by 100, you move the decimal over 2 places, you get 19.95%. So there's almost a 20% chance of getting it in the red area. Almost 20%. Almost 20. 19.95% of getting into the red. The green one, now how do I get the green area in this? What is your plan to get the green circular part? It's just a strip around the red. How do I get that? Make a plan. Why do you think I did pi times 3 squared minus pi times 2 squared? What was I doing here? What does the pi times 3 squared represent? The whole circle. The 3 is the whole radius right here. So you can see that this 3 goes all the way to the edge. That's going to give me that whole circular area. Then what did I do is I subtracted out pi times 2 squared. What does that pi times 2 represent? The red. That's the red one. So I'm going to take the whole thing and pull out the red one. That's going to leave me with the strip, the green. So that gives me 15.71 over 63. Dividing gives me 0.2494. So that's a 24% chance. Almost 25. That's almost a 1/4 chance of hitting the green. So which one should be worth more points? You're making that a dartboard. Which one should be more, the red one or the green one? The red should be more. It's harder to hit the red. You only have a 20% chance. You got a 25% chance of hitting green. They should be close. If you make the red 10 points, then the green should be 8 or 9, because they're pretty close as far as probability goes. The last one is your white probability. You got to find the white area, which is the whole thing minus the circle. The whole circle is 9 pi, or 3 pi times 3 squared. That would give me your 34 divided by 63. That gives you your 55%. What could you do at the end to make sure you did good? Add your percentages. What should they add up to? 100%. You're talking about the whole thing. So those percentages should add up to 100%. What I did is I added them up and I got 100.02. You're going to have a little rounding here and there. It was 100.0. They just had a 0.2 on it, which is okay. So that's geometric probability, something that we talk about when we were dealing with areas. Since today's assignment is on areas, I wanted you to see the probabilities as well, because we need areas to find our geometric probabilities.